So once again, this is Paige Johnson with the American Wind Wildlife Institute. The webinar that we are holding today is new research on wildlife monitoring at offshore wind energy facilities supported by the U.S. Department of Energy. And so for some quick logistics notes, you should be able to hear us through your computer. If you're having any technical trouble with the webinar, you can send us an email at support@kernswest.com, and that email address is in the notes box on your screen as well. You can also send us logistics questions through the Q&A box on the screen, and we'll try to help you out. And I've given a reminder, but please make sure to mute your lines for everybody on the phone, speakers included when you're not speaking, to make sure we don't get any background noise, as that can be disruptive. And if you are dialed in on the phone, make sure also that your computer speakers are muted so you don't get feedback. We will be having 4 presentations today, and we'll have a Q&A session after each presentation. So if you have a question for the presenter, you can enter it into the Q&A box there on your screen on the right-hand side. And what we'll do is we'll read the questions out loud for presenters to respond to, because you'll only be able to see the questions that you entered. And you're welcome to type in questions whenever you think of them during the presentation. We'll read them at the end as time permits. If we end up with any extra time at the end of the webinar, and there are questions that we didn't have time to get to, we can circle back on those, and the presenters have generously offered to answer questions via email if there are questions that we don't get to during the webinar today. And finally, a reminder that we are recording this webinar, and we will post it on the NWCC website along with PDFs of the presentation slides shortly when we're finished with this webinar. So again, today we have presentations on wildlife monitoring technologies at offshore wind facilities. And to begin with, I'm just going to pull up some intro slides that will be presented by Jocelyn Brown-Saracino to introduce the projects. Jocelyn is the Program Manager for Market Acceleration and Deployment at DOE's Wind Energy Technologies Office. So she's going to tell us a little bit about the funding opportunity and the projects that we'll hear about today. So take it away, Jocelyn, whenever you're ready.
Great. Thanks so much, Paige. Can you hear me okay?
Yep, hear you just fine. Thanks.
Okay, great. So as Paige mentioned, all of the projects that you're going to hear about today are supported at least in part by the U.S. Department of Energy's Wind Energy Technologies Office. And as a result, I'm going to provide just a few opening remarks to provide a little bit of context for the broader work that we do within our program, and then specifically the work that we do within our environmental research program, and how the work that you're going to be hearing about today fits within our mission and within the context of that work area as well. So the Department of Energy's Wind Energy Technologies Office works to support, we fund research, and we're working to support advancing scientific knowledge and technology innovation to make sure that the nation has access to clean, low-cost wind energy options. And we have a number of different program areas where we invest in research to advance the state of science and technology. We have a body of work that's really focused on improving wind turbine and wind plant performance. We have a body of work that's focused on grid integration challenges. And then we have a body of work that the work that you're going to hear about today is funded through, that really focuses on addressing environmental and siting challenges associated with wind energy development. And within our program, we fund work through a variety of means. We fund work through direct support of national lab researchers. We fund work through competitive solicitations, and then we also work directly with federal partners and work hand in hand with a wide variety of wind energy stakeholders to ensure that our work is meeting the needs of the broader wind energy community. And the work that you're going to be hearing about today is funded through a compilation of mechanisms, both national lab work, and then work funded through a competitive opportunity. So the program that this work is funded through is a broader portfolio that supports work around siting of wind projects, stakeholder engagement and outreach, and then also our environmental research portfolio. And within our environmental research portfolio, we're really aiming to help develop informed solutions to wildlife impacts from wind energy, both land-based and offshore, and focus through a variety of different mechanisms. We support research to really help us characterize the issues, understand the drivers of risk, and then we support a body of work to develop and improve and validate monitoring and mitigation technologies. And the body of work that we're going to be hearing about today falls within that portion of our portfolio. And then we also support a variety of efforts to really help ensure that environmental research from around the world is made public, is widely disseminated, is easily accessible and synthesized. And at the very end of my remarks, I'll point you to some resources in that regard. So 3 of the 4 projects that you're going to be hearing about over the course of this webinar were funded through a funding opportunity announcement that the U.S. Department of Energy issued in 2018. And that webinar, that funding opportunity had 3 different topic areas, 2 focused on land-based wind environmental research efforts, primarily focused on impacts to bats. And if you're interested in those topics, we will be hosting, in partnership with the NWCC, separate webinars on the work that was supported through those topic areas. And then we had a 3rd topic area focused on the development and validation of offshore wind monitoring and mitigation technologies. And the work that was funded through that topic area is the work that we're going to be hearing about today. And the work that you're going to be hearing about today is largely just kicking off. And so the intent of this webinar and sharing information about these projects is really to make sure that the broader offshore wind community is aware that these research projects are underway, give you a sense of what the anticipated outcomes of the projects will be, and also give you a sense of when results from these projects will be made publicly available in case you're interested in utilizing the results of them. And the projects funded through this solicitation that you'll hear about today received about $2.3 million in DOE federal funding, and with external cost share, the total project value was $3.2 million in total. And then the 3 projects that you're going to be hearing about today funded through this solicitation focus on 2 different areas of environmental monitoring. One led by SMRU, is focused on developing cost-effective and easily deployable acoustic buoys for monitoring marine mammals around construction activities. And then Oregon State University and WEST will both be talking about 2 different approaches to developing collision monitoring systems for automatically detecting when collisions occur with turbines. And then the 4th project that you'll be hearing about over the course of this webinar is a project funded directly with the Pacific Northwest National Laboratory. And this is a project working to develop a camera system designed for tracking bird and bat behavior around offshore wind projects, and being able to do so in 3D and in real time. I did want to mention just a couple other projects that the Department of Energy is supporting in both the technology development and the resource sharing space, in case it's of interest to those folks around the phone. We are supporting a program through our National Renewable Energy Laboratory called the Technology Development and Innovation Program, which supports early stage technology development and validation in conjunction with the resource resources that we have at the National Wind Technology Center. So this allows early stage developers to utilize resources such as access to wind turbines at the National Wind Technology Center to do some early stage testing and validation of prototype technologies. And so if that's an opportunity that's of interest to you, I'd encourage you to check out the website and keep an eye out for periodic competitive solicitations around supporting those sorts of efforts. And then finally, I did want to mention briefly the TETHIS database. The TETHIS database is a database supported by the Department of Energy and hosted and run by our Pacific Northwest National Laboratory. And this is a database that houses, among other things, a searchable literature library on research on environmental impacts of both land-based and offshore wind. Those resources can be viewed either in a traditional database format or in a map viewer. And the TETHIS database also includes information on webinars such as this, as well as webinars hosted by other organizations, events such as conferences and workshops, and a host of other resources. So if you're interested in the offshore wind environmental space and you're not already aware of TETHIS as a resource, I'd encourage you to check it out. And so with that, I'd like to thank you all very much for taking the time to join the webinar today. I'd like to thank the AWWI and NREL teams for their help in planning and hosting this webinar. And I'd like to thank the speakers for their generous commitment of time in presenting today. And if you're interested in learning more about the work that we do more broadly within the Wind Energy Technologies Office, I'd encourage you to check out the website link in this slide. And with that, Paige, I'll pass it over to you to introduce our first speaker.
Great. Thank you so much, Jocelyn. Great introduction. And if everyone would just be patient for just a second while we pull up the slides. First up, we have Matt Johnston from Oregon State University. So Matt, your slides are loading, and as soon as you see them, please go ahead and take it away.
Great. Can everybody hear me okay?
Yeah, we can hear you. Thanks.
Great. So thank you for taking the time to attend. I appreciate having the opportunity to present. I'm Matt Johnston from Oregon State University. I'm representing the work of our team, my collaborator Roberto Albertani, and a growing number of graduate students that contribute to this work. So we're going to be describing a system we're building for detection of collisions with turbine blades, specifically targeted at birds and bats, although that's primarily because those are the smallest objects you might want to detect. This, of course, will detect collisions with any larger objects that unfortunately may hit the blades. So there's sort of three primary parts to this project. As Jocelyn mentioned, these projects are still pretty early, so I'll talk a little bit about where we're headed. So the first goal is collision detection. So this is the ability to detect when something hits the blade, or more likely when the blade hits something that's flying through the air. This uses multiple sensors mounted on the blades and sort of takes advantage of some newer low-power sensor modalities. The other important component to the system is object identification, or more specifically, the ability to grab a picture or a video of whatever it was that struck the blade. And in this approach, we actually put cameras on each blade near the root, sort of facing down the blade, and I'll show some examples of that. But basically, this gives you a picture of whatever hits the blade, and we have some additional cameras and microphones to give a view of the area at the time of collision. And the project also includes phased field-based system validation. This includes testing of the integrated system on a turbine blade on the ground, and then a couple of up-turbine tests. As I mentioned, the reason we can do this now is because the sensors are small enough and low enough mass. Our detection algorithms are taking advantage of more advanced statistical analysis processes, and sensor fusion, which is just sort of the combination of multiple sensor feeds to improve sensitivity and detection rates. Our up-turbine testing is planned for testing at the National Wind Technology Center in Boulder, where we have some experience testing there before. And overall, as this fits into sort of monitoring and mitigation, the hope is that with this or similar successful systems, you may be able to improve site monitoring for wildlife impacts. So to give sort of a cartoon, since we're developing the system now, this comprises a blade-mounted impact detection module. This has a variety of sensors that I'll talk a little bit more about, and it also has a variety of on-blade imagers. Advances in camera technology, all of you have one or more imagers in your cell phone at this point, and that's the same sort of technology we use to put very small, very low-power cameras onto the turbine blades. In addition, on top of the turbine nacelle, we'll have a 360-degree camera that captures a snapshot of everything sort of at or above the plane, and a series of high bandwidth microphones, high bandwidth for high frequency for detecting bat sounds as well as bird sounds. So one of the key features here is that you capture images and video and you save those off only when you have actually detected a collision. So that rather than having thousands of hours of video to look through, this is narrowed down to when objects collide. You can go back and look specifically at that footage. A sensor network that I'll talk about is aimed at enhancing sensitivity, particularly for small mass objects, sort of in the 10 gram to 50 gram range, and larger as well. That is targeted around bat and very small bird collisions. We have a combination of visible and infrared and near-infrared cameras so that this can hopefully operate both in daylight and at nighttime. And as I mentioned, we have additional instrumentation on the nacelle to complement the on-blade system. So this builds on previous work that we've done. It looks like one of these images isn't quite rendering, but this should give a pretty good idea of what we built before, which was a simpler version of what we're trying to build now. So what you see here is up in the upper right, the part that is not quite rendering right, is just a small custom electronics module. It's a little bit larger than a credit card, but that gives a sense of scale, and that includes accelerometers, gyrometers, contact microphone, and all of those are used for collision detection, and then the board sits underneath this and connects to an on-blade imager. So you see down in the center a picture of one of these modules in a just big off-the-shelf commercial housing. It's obviously bigger than it needs to be given the credit card size of the electronics, but it's mounted and points down blade. So this is on one of the GE turbines at the Northwest Wind Technology Center in Boulder. And this is actually attached very well with high-strength, sort of double-strength adhesive underneath. The tape is just for sort of additional security, so we don't want them to fall off turbine during our early testing. If you look over on the left, you see sort of the size of one of these modules, and I'll show another picture of 3 of these mounted. So there's one per blade. There's one camera that looks down the blade and does visible light, and then several sensors that are used in combination for impact detection. So to test this, since we are trying to test collisions in these early tests, we had one module mounted per blade, and we fired tennis balls at the blade from the ground or from a man lift. And as you can see on the bottom right, this is an image of a tennis ball colliding with the blade, and this image is automatically captured. So we're constantly looping video and constantly monitoring for impacts on our sensors, and as soon as an impact is detected, sort of the last 5 seconds and the next 5 seconds, or the last 10 seconds and the next 10 seconds of video are saved off. So you have images that should capture the impacting event. So the project we're working on now builds on this prior work in some very important ways. So the first is aimed at improving sensitivity. So this moves to additional sensors, not just at the root of the blade, but ideally distributed along the length of the blade, and I'll provide a little more detail on that. And additionally, we are enhancing the vision and the vision system in the imaging system. So we're moving from one camera to multiple cameras so that we can do either stereo or multifocal length. And we are additionally investigating both low resolution and high resolution near infrared and infrared imagers for capturing these images at night. The motivation for both low resolution and high resolution is that the low resolution cameras, or what we're calling low resolution, are again comparable to sort of cell phone cameras, so they're still pretty good. and you can get those that work at near infrared. And if that works well, then that is much more size and cost compatible with deployment. However, you could have the ability of putting on a more expensive high-resolution near-infrared or infrared camera if you need enhanced sensitivity or enhanced resolution. We'll be investigating and integrating both of those to find out which you really need. As before, we'll have automated impact detection and image capture. I will point out that we don't include classification at this point, though that could later be built into the system. This saves us off images so that they could be viewed later by an expert to determine what the object most likely was. So I mentioned sort of the multi-sensor network that we're building to improve sensitivity. So this still has a primary detection module that's mounted at the root of each blade, but this also has small, thin, what we call sensor patches. So in the prototype stage, each one of those is sort of the form factor of a deck of cards, but the electronics are such that they would fit in something much thinner with sort of a similar form factor. So we're building these so that they're wireless. They use a combination of batteries and kinetic energy harvesting since the turbine is often spinning. The goal there is to make these so that they would be perpetually operational. And that's one of the things my group works on as a research idea in general, is sort of sensors that can be deployed indefinitely without having to replace batteries. So these have wireless connection back to the root module, and by putting sort of a vibration or impact detection sensor at periodic locations along the blade, we aim to very much improve sensitivity. This would then send an alert back to the root module where the cameras are to save off that video. We envision, of course, for our initial testing, this will all be external, and that could be used for us. That's sort of the only way to test on a fabricated and installed wind turbine. That could also we envision that as one possibility for retrofitting or for temporary installations for sighting or short-term monitoring. These are small enough and they're wireless, so they could also be placed inside the blade during manufacture or before assembly. At least that's one of the long-term goals. So to summarize, we have distributed vibration and impact detection to improve sensitivity. Our targeted detection sensitivity is down to sort of 10-gram objects representing bats and very small birds with greater than 90%. This is, of course, adjustable depending on your allowable false positive rate. And we are investigating on the research side power and communication schemes to minimize the size and volume of each of those sensor patches. So to sort of summarize our targeted technology outcomes for this project, we are currently developing the multi-sensor impact detection unit and algorithms using on-blade training data. So we have previous on-blade training data. This is sort of baseline vibrations as well as impacts that we use to train our algorithms. We'll be aiming for validation of sensitive collisions using our on-blade sensor network through a combination of the root module and the distributed patch modules. One of the outcomes also, as I mentioned, is a determination of sort of the imaging parameters you would need. How good do your cameras need to be, and how many do you need to sort of get full blade coverage, both for objects that may be close to the root and for objects that may be hit closer to the tip of the blade? So what sort of pixel density do you need, frame rate for the speed at which these move, so on and so forth. That's one of our important outcomes as well. Finally, integration of both the on-nacelle and the on-blade sensor modules for deployed testing. And at the end of this, we're aiming for a technology readiness level 7 prototype that has been demonstrated up turbine on 2 separate site tests in spring and summer of 2021. To summarize our development timeline, we're currently working on the multi-camera version of the root module now, and that's in parallel with our investigation of both the low resolution and high resolution visible near-infrared and infrared imagers for pixel density and frame rate. The benchtop validation of those total integrated systems will happen later this summer. So we're moving pretty quickly on that. Similarly, at the same time and in parallel, we're building our distributed impact sensor patch system with a similar development and validation timeline. Our field validation on a ground-based turbine blade is planned for the end of this year, and that, if all goes well, will set us up for our up-turbine testing in spring and summer of next year in 2021. So the goal then for future work would be more minimization of total system size, cost, and complexity, determining how complex it needs to be to really be useful in a commercial setting, as well as long-term validation. So with that, I would like to acknowledge the Department of Energy and specifically the Wind Energy Technology Office for supporting this project. We're very excited to be a part of it, and we look forward to showing results here in the coming months. Thank you.
Wonderful. Thanks so much, Matt. And we have a few minutes here for questions. So if you have a question for Matt, you can type it into the Q&A box, and I will read it for Matt to respond to. The first question that we had come in is related to what you were talking about in terms of coverage and your future steps for commercial deployment. The question is, offshore wind turbines are very large. How large of a rotor could this technology cost-effectively monitor?
Yeah, that's a great question. So we're developing this as a modular system. So we test on just a 1.5 megawatt system. But basically, since it's a distributed patch system, you could just increase the number of patches to get down the length of the blade. And in a future incarnation, since these are all wirelessly networked, they form a mesh network. They could bounce that back up. The issue as you move to larger blade systems is you might actually need to put a camera sort of partially down the blade. But these cameras are sort of, cubic centimeter size, so that might actually be feasible. That's something we haven't looked at. So I don't know the exact answer to that, but it's scalable, certainly by intent or by design.
Great, thanks. We have a couple questions asking about whether the modules affect the efficiency of the turbine. So what are the effects of the blade mounted components on power generation, and do you have a way to assess this?
Yeah, that's a great question. We're looking at ways to assess this by collaborating with other groups who look at sort of blade edge research and efficiency. We don't have a good estimate now of how this would affect the efficiency. I would point out that these are aimed to be sort of, in the long term, like credit card size and 5mm thickness, and you only have a few of them across a very large, 50-meter blade. So we don't expect high efficiency. It would be possible to explore that through collaboration, which we're looking at. We don't have a specific plan to look at that now. In addition, these are meant to be thin enough and wireless enough and easy enough to install that if planned in advance, they might be able to go inside the blades as well, and then there would be no efficiency impact, because the mass certainly is negligible.
Okay, great. That partially answers the next question, which was, is there any need to mount the cameras on the front and the rear of the blades?
That's a good question. That's something we are talking to wildlife biologists a bit about. So for bats, it seems like that might be necessary, and or you can have cameras mounted sort of down at the base looking up, or other cameras on the nacelle. But if you want a picture of the thing hitting the blade, then you'd certainly need a camera on each side. For a lot of these, sorry, to clarify, what we're talking with the wildlife biologists about is for birds if they tend to approach more from one side or the other. But certainly, again, it's modular, and you could put these on both sides with minimal additional complexity.
Thank you. The next question might be a little bit more for Jocelyn. The question is about whether any types of technologies like blade-mounted technologies may at some point be required by BOEM as part of wind farm operations.
Yeah, DOE is not a regulatory agency, and so that's not a question that I can answer or would want to speculate on.
Okay, thanks, Jocelyn. The next question is, do birds or bats have to actually hit the blade for the detections to occur?
Great question. So for the on-blade system, they're set up so that would be the case. But the system could easily be changed, especially with the nacelle-mounted camera. So you can very easily detect motion from the nacelle-mounted camera and use that to start saving off video from the blade imagers as well. So that's not currently on the feature list, but that would be a relatively easy thing to add, but it would produce a lot more video that would have to be reviewed.
Wonderful. Thanks, Matt. Well, we've come to the end of the time we have for this Q&A. We're going to have to jump to the next presentation to make sure we have time for everything. But again, if we have time at the end, we can come back to some of the questions that we didn't get to. And if we run out of time to address all the questions, then I can distribute them to Matt and he can get back to those folks whose questions did not get answered after the webinar by email.
I'd be happy to do that.
Great. Thanks so much once again. And now we're going to move to our second presenter, which is Rebecca Schmidt and Rhett Good with WES. And I see Rebecca on. So Rebecca, we're pulling up your slides right now. And I see them now. So whenever you're ready, go ahead and get started.
Okay, well thank you for the opportunity to describe our research today, Paige. My name is Rhett Good. I'm a certified wildlife biologist with Western Ecosystems Technology. Myself and Rebecca Schmidt, our project manager, will be giving today's presentation. So today we'll be reviewing a project that was recently awarded funding through the U.S. Department of Energy. The title of the project is a multi-sensor approach for measuring bird and bat collisions with offshore wind turbines. This is a 3-year cooperative agreement, and the project was kicked off this fall and is scheduled to continue through 2022. So this is a large collaborative effort with a number of organizations involved. WEST is leading and managing the project. WEST is an ecological consulting firm, and we have experience designing and conducting bird and bat mortality studies, as well as implementing machine learning at wildlife studies, I should say. Another key component of the project, or key collaborator, I should say, is TNO. TNO is a research organization comprised of scientists and engineers who have been involved in offshore wind energy for decades, I believe. They're also the developer of the WT bird system and has successfully implemented the system for detecting bird collisions at offshore turbines. Another important project partner is NREL. NREL is an engineering team with 44 years of experience developing and testing wind turbine technology. NREL will be leading the engineering tests and efficacy tests of the system at NREL's wind turbine facility in Golden, Colorado, and supporting other engineering aspects of the project. The final partner is LEEDCO, the Lake Energy Development Corporation. LEEDCO will be offering the turbines for the proposed offshore icebreaker project as a host site for the final phase of the project. So I wanted to talk a bit about the background and need for the project. While offshore energy is well established in Europe, relatively few of those projects have directly estimated bird and bat mortality rates. Rather, most of those projects model potential mortality rates based on radar data or other metrics. Offshore wind energy is new to the U.S., and while we have lots of studies and have a good handle on land-based mortality of birds and bats at land-based wind projects, some questions remain regarding the level of impact to birds and bats at offshore turbines. Monitoring at offshore turbines for bird and bat collisions offers some obvious logistical challenges. Unlike land-based surveys, we can't walk transects under turbines and document bird and bat collisions. So there's a great need to develop technologies that can withstand the harsh conditions of offshore turbines that offshore turbines face, as well as estimate bird and bat mortality. Kind of the basis for our project is the WT bird system, and the WT bird system is an offshore bird collision detection system that was developed by TNO. It's been in development since 2004, and it was designed originally to detect collisions of larger birds, such as waterfowl or seabirds, during daylight hours. The system is comprised of 2 primary components. One's a series of vibration sensors placed within the turbine blades that detect when something impacts the blades. The second key component is a series of wide-angle, high-resolution offshore-grade cameras that are placed around the base of the turbine that help identify the species that triggered the collision. And the system works such that when the vibration sensor is triggered, the system registers the date and the time and the classification of the event. And then the video images and the sound before, during, and after the event are recorded. The wind farm operator is then notified by an email that a collision has been detected, so they can go back and look at the video and verify, potentially if the species was, what the species was, or if it was another type of collision. This system was attracted to us when we were examining potential research options because it has already been deployed for multiple years at offshore turbines in the Netherlands and has successfully documented large bird collisions. So the engineers at TNO have already gone through some of the trials and tribulations of finding hardware that can withstand offshore conditions. The primary goal of our project is going to be to work with TNO and NREL to improve the WT bird system to be able to detect small bird and bat collisions during both the day and night. One of the more interesting aspects of the project is we're going to attempt to integrate machine learning into the video portion of the system to automatically classify collisions to species or species groups such as small birds, large birds, and bats. I would say similar to human-based carcass searches under land-based turbines, we don't expect the system or any system to detect all collisions at the turbines. An important aspect of this project is we're going to try to attempt to estimate the detection probabilities of the system so that mortality rates of birds and bats can be estimated based on the number of detections from the system. The system also has potential applications to land-based turbines. One, you could use it to estimate mortality on land. I think a more potentially intriguing use would be to identify the time of death of a bat collision, which could be used to potentially develop smarter curtailment regimes for land-based wind projects. The DOE's goal for this project is to promote technologies and support the advancement of offshore wind in the U.S. And I think this project could potentially help meet that goal by providing regulators and scientists the tools they need in order to evaluate the impacts of offshore turbines to birds and bats.
Our project will be carried out in 5 major phases throughout the 3-year project period. The first 3 phases of our project will include the engineering and initial testing of those improved vibration sensors at TNO's facility in the Netherlands, followed by more intensive testing and refinement of the technologies at NREL's facility in Colorado. And this is when we'll really start to integrate the machine learning work. The final 2 phases of the project will include validation testing at a land-based turbine. We'll also be conducting concurrent on-the-ground carcass searches to help verify the results of our system. And finally, full system implementation will occur at an offshore wind turbine. Again, one of the major advancements of this project will be to enhance WT birds vibration sensors to detect those smaller objects. So TNO will be carrying out a set of tests using objects of different sizes and weights that would resemble small bird and bat characteristics against a stationary blade on the ground at TNO. And the table presented here gives you some approximate weights of the sizes of objects that we'll use to resemble some possible target species. When the improved sensors have met a set of success criteria for detecting those smaller objects, we'll install the system at NREL, where we'll conduct more intensive testing regimes and sort of fine-tune the system for optimal performance. At this stage, we'll also be figuring out the best placement for cameras, whether that's on the base of the turbine or the nacelle or both, for collecting the imagery data needed to advance the machine learning work. Again, the second advancement of the project will be to integrate machine learning. So now we have enhanced vibration sensors that can detect smaller bird and bat collisions while also minimizing false positives. We'll be recording those collision events using high-resolution cameras. And the machine learning algorithm at that point, which is developed and trained by West, will then process that imagery data and identify and classify the objects. The main objective of the machine learning work will be to classify to species or species groups. And of course, this classification will be based on a number of physical characteristics such as shape, size, color, flight patterns of the birds and bats that's being recorded. We'll have verification tools to make sure the machine learning algorithm is working and classifying objects correctly by manually reviewing the camera footage and through use of acoustic detectors. The final phases of our project will include full system validation at a land-based turbine. As a side note, we're still seeking out a host site for this effort. West will be conducting concurrent on-the-ground carcass searches to compare the fatality data with the results of our automated system and classifier. We'll also be collecting acoustic bird and bat data at the site to help verify those species classification. And this will really be one of the major undertakings of our project in making sure the system is ready to deploy offshore. The final phase of the project will hope to validate the effectiveness and readiness of our technology through implementation at an offshore wind turbine, and that's currently planned for LeadCo's proposed Icebreaker Wind project in Lake Erie. Our proposed timeline for completing this work is outlined here. Those initial engineering, testing, and refinement of the system components at both T&O and NREL will be completed in the first half of the project. That work is expected to go through spring of 2021, at which point we hope to be able to install the system on a land-based turbine. We plan to test the full system at a land-based turbine for a full year and hope to have final system implementation at the offshore turbine by fall of 2022. Again, we'd like to thank DOE for providing the funding for the work. We're excited about the possible advancement of the monitoring technologies developed through this project and how it can help inform bird and bat impacts at offshore wind farms. If you have any questions, we're happy to answer those at this time. And also, if you're interested in being a host site for our land-based installation, you can contact me or Rhett at the email addresses listed here. So thanks again for listening in, and we look forward to answering your questions.
Thanks so much, Rhett and Rebecca. So, yep, a reminder, we have a few minutes for questions here, and we've already got some questions coming in. The first question is about the machine learning algorithm, and it says, is the machine learning from the base-mounted cameras, or will there be other cameras operating on site? So I think it means, is it using data from just base-mounted cameras, or will there be other cameras collecting data?
It's a very good question. So that's part of what the testing is going to involve at NREL, is we're going to test the, the field of view and the various camera models from the base of the turbine, as well as the nacelle. We weren't sure if we could get the resolution we needed from the base, so we're going to test some applications on the nacelle as well to kind of examine the trade-offs between the cost of mounting on the nacelles versus increased resolution to be able to ID the species. So we'll be testing both, but the final determination, I guess, will depend on those balances between the trade-off on cost and resolution.
Great, thank you. The next question is also about machine learning, and is asking if the machine learning algorithm will be able to evolve or learn to identify birds to a species level and potentially be used to trigger curtailments in the presence of threatened and endangered species? And if this is possible, how many years of data would be needed to look at these rare events?
Yeah, those are very good questions. You know, we anticipate like some of the collisions, it's probably going to be unlikely you could ID the species. You know, but the system is originally targeted for, you know, IDing the at least species groups, small bird, large bird, bat. We are proposing to test concurrent use of other detection systems such as acoustics to gain inference on what might have collided with the turbine. You know, for example, something that collides in the day closer to the camera, you might very well be able to ID by species. Something that collides at night with lower, you know, less resolution, grainier images, you may not be able to ID the species. It might just be to a group such as passerines or large birds.
Thank you. The next question is asking specifically, as you were mentioning, looking for a host site, and they're asking if you were aware of Virginia's offshore wind research lease that's looking to have installation this summer, and if you are aware of that and have considered that for a validation site.
I was not aware of that project, so that might be something that we could follow up with whoever asked that question later and get some more information on that project.
Sure. And the person who asked the question, Laura, if you would just respond in the Q&A box and let me know if you're the correct person to follow up with, and I will put you in touch with Rhett after the webinar. Let's see, we've got more information coming in that it's a Dominion Energy offshore wind project. So I'll try to connect you with some folks who might be able to tell you more about it. All right. Are there any other questions? We're right about at the end of our time. We have time for one more question if anybody has anything burning. Okay. Well, thank you so much, Rhett and Rebecca. Very interesting. And we are now going to move on to our next presenter. We have, sorry, I'm pulling up the presentation now. We have Shari Matzner from Pacific Northwest National Lab. And give us just a second while the slides load. All right, so the slides are up. Shari, take it away whenever you're ready.
Great. Thank you so much for the introduction. My name is Shari Matzner. I'm with the Pacific Northwest National Laboratory, and I'm going to talk about a technology we're developing called ThermalTracker 3D. So the purpose of this technology is to provide site-specific detailed information on seabird and potentially bat activity. It's meant to complement aerial and ship-based surveys. So those methods have been used for quite a while, and they are great for providing large area data on bird populations, their movement patterns, where they go and when, and so forth. But this technology is aimed to provide more detailed information for a particular site by being able to record continuously both day and night and in most weather conditions. And really the overall goal of developing technology like this is to reduce uncertainty during the siting and permitting process. So be able to provide a way to collect information at a site pre-construction when there's no infrastructure available, especially at some of the proposed sites off the west coast of the U.S. and the east coast that may be too far from shore to allow using some existing technologies like shore-based radar or shore-based LiDAR. And then also the goal is to collect data that will improve the accuracy of collision risk models. Collision risk models are a key tool that are used by regulators when they're making siting and permitting decisions, yet there is a lack of empirical data to really validate and refine these models. So as the U.S. moves forward with developing offshore energy resources, BOEM, the Bureau of Ocean Energy and Management, is the federal agency that controls the lease areas. And these are the guidelines that they provide for avian surveys offshore. And the ThermalTracker 3D technology is aimed to support each of these bullet points here, but really especially the second bullet and the last bullet. So this technology can be used for pre-construction baseline data and then could also be used to monitor operations post-construction. And there's a huge advantage of being able to use the same technology for the baseline and the operational monitoring in order to quantify any changes in behavior, because then the comparison will be apples to apples. The ThermalTracker 3D system works like this. It consists of a stereo pair of thermal cameras, and we use thermal cameras because birds and bats are fairly easy to detect in thermal imagery, and also because it's effective both day and night. The cameras continuously record video, and then the software, this is where the bulk of the research has gone into, is developing and refining these algorithms that automatically extract the flight track information from the video in real time. And then that extracted information is transmitted back to shore, and that can be transmitted periodically every hour or daily, depending on what the project needs are. And the information that I'm showing here was actually made up, but it illustrates the type of information that is collected by the system. This is more of a summary of observations where each row represents the flight of an individual bird or potentially a bat. And then the details of the three-dimensional flight track of each animal is also stored, and that can be visualized in a geospatial application like Google Earth or ArcGIS. The components of this system are fairly simple. It's mainly a stereo pair of thermal cameras, the software, and then of course the software needs a computer to run on, and we just need a data link and some sort of power. And we've actually been developing this technology for several years now. We completed a land-based validation this past summer, which I'll tell you more about, and we are planning to do an offshore validation this summer. And then as a result of what we learn from those two validation exercises, then in 2021, we plan to refine the operations and further mature the technology. So last summer at NREL's National Wind Technology Center, we did a land-based validation in order to evaluate the accuracy of the three-dimensional position estimates. We used a drone. You see a picture of it there. It's called a Firefly Pro. The wingspan is approximately 1 meter, so it's similar in size to like a medium to large-sized seabird. And the drone, of course, is equipped with GPS, and it flew various flight patterns mimicking different kinds of bird flight. And we were lucky enough to experience many different weather conditions during the testing, everything from blue skies, sunny days to lots of clouds and even snow. This is the prototype that we put together for that testing. The total cost of it was about $25,000. It used FLIR A65 thermal cameras. They're a fairly inexpensive type of thermal camera, and we built this custom platform to mount the cameras on, and it allowed us to adjust the height of the cameras and also the orientation of the cameras relative to the horizon, so we could evaluate different viewing angles and how effective that was. And then we just used a high-end laptop to run the software, and we used the power and data that was available at the site. To evaluate then the accuracy, basically we took the GPS data from the drone, we converted that into a common coordinate frame that's shown there, and the coordinate frame we used had the Y dimension basically be the flight height. So the Y dimension is the flight height above the surface of the Earth. And then we interpolated the GPS data to the same times as our position estimates, because we were estimating at 30 frames per second. And then we just looked at the error in each of those dimensions. And if you look at the Y dimension there, you can see for the most part, the estimates from the ThermalTracker 3D were within 5 meters or so of the actual flight height based on the GPS. So that accuracy we feel is sufficient for collecting useful data. Now, this spring, the plan is to deploy offshore. The ThermalTracker 3D system will be integrated with a Wind Sentinel buoy. There's an illustration of one. DOE owns 2 of these buoys, and BOEM will be deploying them off the coast of California. We'll be integrating our system on the buoy that'll be deployed in the Humboldt call area. This is 25 nautical miles offshore, so pretty remote. The deployment is slated to last for 1 full year, and during that time, we will have ship-based surveys, so we'll have some observers go out to the buoy location and make observations of seabird activity, and then that data can be used to validate the data collected by the ThermalTracker. And the great thing about integrating with the buoy is that the primary mission of the buoy is to record data on the wind profile. So it measures the wind speed and direction not only at the surface, but all the way up to hub height and beyond, so up to about 200 meters. So all that wind data will be able to correlate that with the seabird activity data that we collect, as well as other environmental data that the buoy is instrumented to collect. There's 2 primary technical challenges to this, one being just the harsh environment. So anyone who's done any work offshore knows how hard the marine environment can be on equipment. So that will need to be addressed. And then also the platform motion. So the buoy will be rocking and rolling with the waves, and we'll need some way to stabilize our camera system so that we can obtain good quality video and so that the algorithms will continue to be effective. This data that is shown here is from previous deployments of the Wind Sentinel buoys off the east coast of the U.S., and you can see there's a fairly significant amount of pitch and roll. So this is the prototype that we're in the process of putting together for that deployment. We'll be using the same cameras that we used for the land-based, and but using stainless steel housing. We're adding a visible spectrum camera and some additional instrumentation, IMUs, to measure the exact precise motion of the cameras, and a GPS mainly for time synchronization so that we can sync up the data that we collect with the buoy instrumentation data. And then for the stabilization piece, we'll be working with a company called Perfect Horizon, who has developed a system you see pictured there. It was originally developed for the film industry, but specifically for marine applications. And the company also has experience stabilizing other sensors. And so we're really excited to have this solution. And finally, we'll also be updating our software to correct for any residual motion that's not compensated for by the stabilization system, and make sure that our algorithms and everything is just robust enough to operate long-term unattended and can recover from any errors that might occur. So in summary, this technology is designed to collect site-specific activity. It can be used for baseline data collection as well as operational monitoring. And the main goal is to collect empirical data that can be used to reduce uncertainty, improve our understanding of the effects of offshore wind on seabirds. And with that, I would like to acknowledge and thank DOE for the funding of this work, and thank you all for your time. And yeah, please let me know if you have any questions.
Wonderful. Thanks, Shari. We have a few questions coming in. There are a few questions about when this is past the testing phase, when it's actually being executed for site assessments. Would there be any point at which the camera system would be mounted on turbines directly? Do you foresee this being installed on the Met buoys or Met towers during the actual site assessment activities? What would that look like?
So if I'm understanding correctly, this is regarding pre-construction monitoring or post or both. For the pre-construction, yes, the point of what we're going to do this spring, integrating with the buoy, will help us see how well this will work on such a platform. And this is actually probably a more challenging platform, the buoy is, than say a Met tower or an actual turbine that would probably be a lot more stable. So any of those things are also a possibility. And then during the operational phase, when turbines are present, if there is a Met tower, that could be potentially used, or the equipment could be installed at the base of the turbine. So there's definitely flexibility in where the cameras could be positioned.
Great, thank you. I think that answered the multiple questions that were asked. If anyone has any follow-up questions, then go ahead and let us know. The next question is, what is the detection range of the thermal camera? And the second part of the question is it able to ID bird species? Is it able to identify birds of the species group, and if so, how?
Yeah, that's good. So the detection range is out to, again, depending on the size of the bird, and this is based on the current cameras that we're using. Larger, medium to large birds, probably out to 400 meters, can be reliably detected. Smaller birds out to about 300 meters. So it's not, the detection range is not as far as something like a radar or a LiDAR. There is a little more detail, though, provided by the thermal imagery, and so it does allow us to do some kind of taxonomic identification, maybe not down to the specific species, but what we can do is look at the flight pattern itself is one clue, and we've published some work on using the flight patterns to do identification. And then we can also estimate the size of the bird in certain cases. So we can estimate the wingspan and the body length using the stereo vision, and then that provides additional clues that help us identify the species.
Great, thank you. The next question is, how does the camera deal with salt spray on the lens?
Right. So that the enclosures that we'll be using, they do have both a wiper and then also can like blow air that clears any debris off the lens. So we're going to have to keep our fingers crossed and hope that that is sufficient. But that's part of what we'll learn during this first offshore deployment.
All right, thanks. The next question is, would it be possible to deploy acoustic bat detectors on the wind buoy alongside the thermal tracking equipment?
Yes, that's a great question, and in fact there was some discussion about potentially doing that for this deployment, and I'm not sure if that's going to happen for this deployment, but I think it's a fantastic idea. Acoustic data would really complement the thermal data, especially if there is any bat activity out there, and I think that's a really big unknown right now. And so although we could get some visuals of the bats if they're present, acoustics would really add to being able to identify the species of those bats. So I think that would be a great idea.
Great, thank you. We have time for one more question. Let's ask you the last question, which is, what is the area that's going to be surveyed in this project?
Yeah, so it's the Humboldt Call area, which is off the coast of Northern California. The buoy itself will be just moored in place in one location, and as the buoy, you know, it will move around while it's moored. So even though it's moored to the bottom, it will move around in, I don't know, a circle that's maybe, you know, 100 meters in diameter. It'll kind of move around within that space, and so the cameras will look at different parts of the sky while it's out there.
Great, well thank you so much. We're going to have to move on to our last presentation. So once again, there's a few questions we didn't get to, and we'll try to get to them either at the end of the webinar or offline by email afterwards. So thank you, Shari. Our next presenter, our last presenter, is Jason Wood from SMRU Consulting. And once again, give us just a second to pull up the slides. All right, so I think we're ready to go, Jason, whenever you're ready.
Hi, can everyone hear me?
Yep, coming through loud and clear, thanks.
Great, thank you so much. And first of all, I just wanted to thank NWCC for setting up this webinar and for allowing me to speak. So I'm going to be talking about our project. It's called the Acoustic Buoy for Offshore Wind, or CABOW. And just as a little bit of background, SMRU Consulting is the lead entity on this project. We are a commercial offshoot of the University of St. Andrews in Scotland, with offices here in the U.S., in Canada, Hong Kong, and also in the U.K., obviously. We're taking the lead on this, doing most of the development, the lab testing, the field testing, etc. Some of the key collaborators on this, though, are some folks at the University of St. Andrews that will be helping us with the detection some of the detection, classification, and localization work and software, and then also our sister organization, St. Andrews Instrumentation Limited, which will be helping us with some of the internal electronics. Okay, so the talk is, I'm going to talk a little bit about some of our current technology that's forming the basis of this project, and then I'll present the goals of the CABOW project, our research plan and timelines, and hopefully with some time for some questions. So over the last 3 or 4 years, SMRU Consulting has developed the Coastal Acoustic Buoy, or CAB, and it's really aimed at coastal activities that require marine mammal mitigation using passive acoustics. So these are just passive hydrophones that we're using. There's no active acoustics involved. So it does require the marine mammals that we're trying to detect to actually vocalize. And this is really all geared towards trying to mitigate or monitor for marine mammals around potential construction activities and other activities that generate underwater noise and may cause concern for potential impacts on marine mammals. And one of the key design criteria from our point of view was to try to incorporate a system into a platform that was cost-effective, and part of that being cost-effective was being able to be deployed by 2 people from a small vessel in coastal waters that would all help make it flexible so that it could be used and deployed in a number of different ways, and then also to control costs. And this has been developed with some internal electronics from our sister company, the St. Andrews Instrumentation Limited, as well as in collaboration with the Applied Physics Lab at the University of Washington, who helped us design the actual platform and structure and some of the more. The CAB unit, as I said, is small, so it's less than around 100 pounds. We use a high-quality rezone hydrophone. It's moored in place. We've also deployed it floating as well. We typically use comms. So basically the processing happens on board. Depending on the modules that we put on, we can measure ambient noise levels in a bunch of different ways, either broadband, third octave band, in specific frequencies. We can calculate sound exposure levels. And then we can also run detectors. If anybody's familiar with the PAMGuard software, it's basically running those detectors on board. So we have a whistle and moan detector, which detects tonal calls from marine mammals. And then there's also a click detector for detecting echolocation clicks. And because the soundboard, the DAC board, can digitize up to 500 kilohertz, we can detect marine mammals, any marine mammal that's vocalizing, so down from baleen whales all the way up to harbor porpoise, which are echolocating up at about 130 kilohertz. Most of the time we're running the detections in real time and sending those data either via a radio link or cell. And if need be, we can also record the data on board for later post-processing, and that's currently at a technology readiness level of 9. So this forms the base technology for the CABOW project. And specifically, the goals for this are really geared towards developing a cost-effective and robust system for monitoring and mitigating around U.S. offshore wind construction, largely because of concerns about potential impact pile driving noise on marine mammals and specifically North Atlantic right whales. And so the 2 key goals are, one is to provide an efficient way to validate acoustic noise modeling. So before construction happens and before the project is permitted, usually acoustic noise modeling is done to estimate potential zones of impacts on marine mammals. And the requirement usually is within the first stage of that project to validate that noise model. And so the idea with the CABOW project would be to provide a platform and technology that would help validate that in the first few days of the project and do that efficiently and quickly. And then be reconfigured, basically moved around so that then it would then provide a system to monitor exclusion zones for North Atlantic right whales. So the basic research plan is split up into these 3 main stages. So the first portion is lab-based and desktop modeling and testing, at the end of which we're hoping to get to a TRL of 4. and I'll show you the timelines for this later in the presentation. That's then followed up with a phase where we're field testing and validating in Washington State waters, both on inland waters and offshore, and I'll talk a little bit more about that briefly. And we're during that phase, we're hopefully transitioning from a TRL through a TRL of 5 and 6. And then the final phase is an effectiveness trial in Maryland offshore waters that will hopefully take us to a TRL state of 7. So in terms of the lab and desktop modeling, there are a couple things that we're focusing on. One of the key things here is there's we could make a very complex and fancy system to get this done, but our goal is to try to keep things as simple as possible so that they're as robust as possible and so that they're as cost effective as possible. So one of the considerations that we're going through is whether or not we use, say, for example, a single hydrophone on each buoy or 3 hydrophones on each buoy for the localization processing of the North Atlantic right whale calls, or whether we use pressure sensors, so typical hydrophones, or whether we use particle motion sensors to help in localizing where these calls are coming from to determine whether the whale is inside or outside of the exclusion zone. And as a background, the exclusion zone size is quite ambitious in the sense that currently that exclusion zone is on the order of 10 kilometers. So it's not an easy task, I guess I would say. The other issue that we're also addressing, will be addressing in this phase are the comms. So while we process the data on board, we still need to send the results in real time to the potential marine mammal monitors on a construction site to let them know whether or not the construction needs to shut down because the whale is within the exclusion zone. To date, we've been using radios, and specifically 900 megahertz radios, as well as cellular, and we will likely also need to spend some time looking at options for satellite comms as well. They all have their pros and cons. Bottom line is, sending data over water is also not a trivial task, especially when you're talking about exclusion zones on the order of 10 kilometers. Phase 2 is the field testing and validation in Washington waters, so it's going to be a big part of our effort. And a big part of it is quantifying the call detection range, and as well as the precision and recall for the exclusion zone. So precision is basically, so this is the proportion of times that the system has said that an animal is in the exclusion zone, and of course the proportion of time that actually really is an animal, whereas the recall is the proportion of times of all of the times that an animal was actually in that exclusion zone that the system has actually picked up. And just to be clear, we'll be doing this. There are no North Atlantic right whales also in Washington waters. We're going to be doing this using playbacks so that we know when and where a quote-unquote animal is. We also need to quantify data transmission and delay and the rates that it's being sent, and we'll also be spending a considerable amount of time mooring on the mooring systems to make sure that we're minimizing noise and that the systems are actually holding in place. And we'll do all of this quantification under a variety of different conditions, winds, waves, and currents, and also ambient noise levels. We have a fair amount of vessel traffic in the area, and wind and waves will also cause some noise, as do currents. Let's see. So I will speed up here a little bit. So the initial testing will be off of, we're based in the San Juan Islands. We'll be testing where that arrow is on some of these banks and depths of 50 to 100 meters. And then some of the final testing will happen out here off of Nia Bay, off the outer coast, where conditions in the summertime are comparable to conditions on the East Coast at offshore wind sites. And then the final test will happen on the East Coast in one of the offshore wind sites off of Maryland, where a third party will be running the systems and will be blind to when we are playing back the sounds and where they're being played back from, so that we can quantify all of these again, quantify the costs of the CABOW system, and then report on all of that. In terms of timelines, the lab testing of the phase 1 is going from what started in August, and we're going until April 2020. Field testing and validation will be a year long, from May to May of 20 to 21, with the effectiveness trial in sort of late summer of 2021, and then final analysis and reporting out at the end of 2021 and into the summer of 2022. And so to end that, I'd just like to gratefully thank and acknowledge the DOE and specifically the Wind Energy Technology Office, as well as the Maryland Department of Natural Resources, who have both provided funding for this, and then open it up for questions.
Great, thanks so much, Jason. And we do have a few minutes here for questions. The first question is, and you talked about this a little bit, can you clarify, can the CAB system localize?
So the current technology, we've deployed it with up to 2 hydrophones at this point. There is software on there that can calculate bearings, and on the base station can then localize. But localizing is a broad term, I guess I would say, and so it's highly dependent on the species, the sound, etc. So the CAB itself, we've not yet used it for localizing marine mammals.
Okay, thank you. The next question is, how is this different from existing passive acoustic receivers? That's a great question. There are a number of passive acoustic devices that are out there on the market. Many of them are archival in the sense that you deploy them and you have to wait until the data, you go retrieve the units to get the data. So this unit is one that works in real time or near real time. There are other units that have been placed on other platforms, including buoys, wave gliders, and slocum gliders that can work in real time or near real time. I think the main difference in our units that we've really tried to emphasize is that we're trying to control costs. So a lot of those platforms are fairly costly. All right, and this question follows up nicely. Any rough ideas for the cost of the unit and data processing? And I know that this is part of these projects is to make sure they're cost effective and to come up with information about that. So I'll leave that open to Jason and Jocelyn if you have anything you want to jump in about as well.
So this is Jocelyn.
Jocelyn, I don't know if you want to answer that. I mean, basically,
sure,
go ahead. Is that Jocelyn?
Yeah, it is. So I'll just say at a high level that, as Paige said, one of the goals of funding under this solicitation was to support technologies that are not only effective from a biological and from a monitoring perspective, but also cost effective. And one of our goals of the end reports of these projects is to not only contain information around the effectiveness of the technologies in terms of detecting wildlife and other performance variables, but also to contain some information on anticipated expensive systems. And for most of these projects, since they are in kind of prototype form, cost is a question that they're still trying to work out, and kind of end cost of final systems is somewhat TBD. But Jason, in terms of any particulars that you want to add for your project, feel free to chime in here.
No, I think that covered it well, Jocelyn. Thanks.
Great, thanks both. The next question is about what you were talking about, having to shut down construction to alleviate trauma for whales. Is there any way, and the question is kind of asking how that would be monitored and enforced, and I don't think that we can really speak to that from a regulatory standpoint, but is there any way that the CABOW system could help to monitor when the whales are in the exclusion zone and then keep up with that monitoring to inform the construction shutdown and then have the construction restart?
Yeah, I mean, I think I'm understanding the question correctly. I mean, that is one of the two main goals of this project, is to be able to monitor when a whale has entered that area, that exclusion zone, so that construction activities can cease, and then continue monitoring to make sure that the whale has been left before the construction activities start up again. And in terms of auditing, I mean I think that was part of the question. There are strict regulations in terms of these construction protocols and the permits for doing them, and that all the CABOW data then becomes part of that sort of audit trail of when an animal was determined to be in the area, what actions then happened after that, and then and so forth. Hopefully that answers that question.
Okay, as far as I understand it, I think you answered it perfectly. And if anyone has any follow-up to that, or it wasn't addressed exactly as you meant it, just let us know. All right, the next question is, how confident are you that the playbacks realistically simulate a northern Atlantic right whale?
Yeah, that's a great and very valid question, and that's one of our key parts and one of the key deliverables on this project to the DOE is to show that we can actually accurately produce a playback of North Atlantic right whale calls. Because if we can't do that, then it makes it much more challenging for us to actually validate and quantify the effectiveness of this system.
Great, thank you. The last question we have for you, Jason, although it's a bit outside of the scope of this project, but I'll go ahead and open it up to see if you or anyone else has an answer. Are there any opportunities or plans to use deterrent technologies for North Atlantic right whales and potentially other marine species?
I don't know specifically for U.S. offshore wind. Certainly acoustic deterrent technologies have been used as part of the mitigation strategies for some projects around the world. So it's potentially an option. Also in terms of pile driving, there's in some ways a typical approach has been to use what's called a soft start approach on the pile driving, where an area is monitored for half an hour. And I'm specifically referring to marine mammals now. An area is monitored for half an hour to make sure that no marine mammals are there before pile driving starts. The pile driving then starts sort of a slow ramp up in the hopes that in case there are any marine mammals in that area, that they're first exposed to fairly or relatively lower levels of sound, and that works sort of as an acoustic deterrent in of itself, and hopefully moves the animals out of any potential areas of harm. But other than that, I don't know of any specifics on using deterrents for U.S. offshore wind.
Great. Well, thanks for filling us in on what you do know. I would direct folks, we've gotten a few questions throughout the webinar that we haven't had time to get to, but a few questions that are more about wildlife, bird and bat, collisions, and interactions with wind turbines more generally that I think are a little bit outside of the scope of these presentations. there is a recent paper that was published in the Ecological Society of America publication Issues in Ecology that is a consensus, scientific synthesis of everything that is known about wildlife interactions with wind energy in the U.S., both onshore and offshore. So I would direct people to that publication, and when we update the website with the recording of this webinar and the presentations from this webinar, I'll include that link. I think that's a good resource for folks who just have questions about bird, bat fatalities, and other wildlife interactions with offshore wind is a good place to start. So we're right at the end of our time. I'll wrap things up. A big thank you to our speakers today. Really interesting hearing about the work that you're doing and these really interesting systems and technologies, and we look forward to hearing more about them in the future when you have some results from your studies. Thank you, Jocelyn, for joining us and telling us more about the program. And just to let everyone know, we are scheduling 2 more NWCC webinars in this series on the other topic areas Jocelyn discussed, smart curtailment and deterrence for bats. So please watch for announcements about those in upcoming NWCC emails. And that is it. We are all wrapped up. So thank you, everyone, and goodbye.